my name is Mackenzie Maxwell, and this is my lab for circuits. The purpose of this lab was to use the principles of energy and current conservation to observe loop and node rule. This was to predict the behavior of circuits in a series and in parallel, and to examine the behaviors of ohmic resistors and capacitors. We will use multimeters from an online simulation to measure actual values of current and potential differences. And these actual values collected from the online simulation are the same as those predicted from the formulas. So loop rule and node rule are supported through experimentation. These are the fundamental principles used in this lab. We have loop rule, where the potential difference of the capacitor plus the potential difference of the resistor R is 0. Node rule, where the I of the resistor in and the I of the resistor out equal each other. And Ohm's law, where we have the potential difference of the capacitor, which is Q over C, and then the potential difference of the resistor, which is I over I times R. This was the first part of the lab. We had charge conservation and energy conservation in a series of circuits. The prediction was the node rule, which is I1 is equal to I2, which has to do with the resistors. You can see in the diagrams to the right of my two experimentation. We have the experimentation with the 2 ammeters, which I equals 0.02. The sign is negative when the ammeters are reversed. And then we have the experimentation with the voltmeter replacement, where we have the voltage equal to 3 volts and the I is equal to 0 amps. The open circuit results in no current measured. However, the potential difference remained constant, which is 0. Here is another experimentation. We have the path calculated, or the potential difference of the path of A to B, and then we have B to C, D to C, and so on. The calculations, all of these do add up to 0, which is the round trip potential difference, which is 0 volts. This is further illustrated on the graph above with the red line. We have the batteries adding 3 volts to the circuit, and then as time goes on and passing both resistors, the voltage of the circuit goes back down to 0. The batteries have a positive potential difference, while the resistors have a negative potential difference. The wires have a negligible potential difference, since we use an online simulation where there is no resistance on these wires. In real life, there would be. We can see the calculations for R for each of the components of this circuit. And when another ammeter is added parallel to the 100 ohm resistor, the overall current increases to 0.06 amps. For the RC circuit, we have some observations. With the battery, the light bulb lights up and dims until no light is observed. This means the capacitor is charged at this point. For the 10 ohm light bulb, which is pictured to the right, it took around 10.1 seconds to complete charge. And then for the 20 ohm light bulb, which is not pictured, it took around 22.3 seconds to completely charge. Then without the battery, once the capacitor was completely charged, the light bulb lights up until the capacitor is fully discharged. For the 10 ohm light bulb, which is pictured, it took around 11.2 to completely discharge, where the light bulb was completely dim. And for the 20 ohm light bulb, it took around 22.5 seconds to completely discharge. For the time-dependent model, we have a graph to the left plotted in Excel of each second and the voltage of the voltmeter. We have then a slope to have the RC calculation, which is 6.17 seconds, which would be 1 over the slope of the graph, and then with the experimental value, which is 30 ohms times the 0.2 Faraday, which is around 6 seconds. From this experimentation, the node rule and the loop rule are supported, and the RC is dependent on time. Some sources of error include theoretical data via the online simulation are not accurate in real-world scenarios. There could be inaccuracies in the voltage measurements, the inexact discharge of the capacitor, and also human error, which could have been from timing off of the stopwatch and rounding when we were calculating our values. What if we were doing this lab in real life and used an actual ammeter instead of the ideal ammeter, which was in our simulation? If the lab were to use this actual ammeter, the current reading would be slightly lower because the real-life imperfect ammeter would have a slight resistance. The simulated ammeter was assumed to have resistance of 0 ohms. And theoretically, without a resistor, the capacitor would be fully charged instantaneously, but in life, wires carry a slight resistance, causing the capacitor to charge more slowly.